Hi, thanks for joining me. Today I've got a quick number theory problem I want to share with you. We want to find all positive integers a, b and c such that 2 to the power of a plus 3 to the power of b plus 1 equals 6 to the power of c. Okay, so if you know how to go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so with these sorts of problems, you'll generally either have finitely many solutions, in which case after some sort of cutoff point which you need to find, there'll be no solutions. So you know that any solution will be beneath that cutoff point, so you just check beneath that cutoff point. Or there are infinitely many solutions, in which case they'll generally sort of follow some pattern. So you can sort of perhaps play about and find that pattern. In this case, we only have finitely many solutions. So what we want to do is find some cutoff point and then notice that after that cutoff point, there can't be any solutions. Well, how do we go about finding that cutoff point? Well, the answer is just generally from experience with problems, you know kind of what to try. But in this case, what we're going to do is look at this equation here, mod 8. Okay, so we're going to look at it mod 8, and we're going to suppose that c is at least 3. And what we're going to show is that there are no solutions when c is at least 3. So then that will be our cutoff point for c. So then we know that c is either 1 or c is either 2. But let's firstly show that. So suppose c is at least 3, then what we're going to do is look at both sides mod 8. So if c is at least 3, well, if we look at both sides mod 8, this guy here will be 2 to the c times 3 to the c. But since c is at least 3, 2 to the c is going to be some multiple of 8, and thus the right hand side will be congruent to 0 mod 8. So that right hand side is always going to be congruent to 0 mod 8. Now let's look at the left hand side. Well, if the left hand side, if we have a, if a is at least 3, then we know that 2 to the a is going to be a multiple of 8, and thus be 0 mod 8, so that is going to be 0. And then 3 to the b plus 1 is all we're left with on the left hand side. So the left hand side is just congruent to 3 to the b plus 1, and the right hand side we know is congruent to 0 mod 8. Okay, so we have 3 to the b plus 1 is congruent to 0 mod 8, but if we look at 3 to the b, well, the reason we actually chose mod 8 is because it works nicely in base 2, but it also works quite nicely in base 3. Because if you look at the number 3, that's 3 mod 8, but then if we look at 3 squared is 9, which is 1 mod 8. So that means that we go back to 1. So then that means 3 cubed is going to be 1 times 3 mod 8, so 3 mod 8. And then 3 to the power of 4 will be 1 mod 8. And in particular, 3 to the power of n, or in this case 3 to the power of b, will be 1 if b is even, or 3 if b is odd. So it only takes 2 values. So this guy here is only ever 1 or 3. So that means this left hand side here is, if we add 1, is going to be 2 or 4. But notice that in both those cases, we're never equal to 0 mod 8, and that tells us that there are no solutions. So if c is at least 3 and a is at least 3, then there are no solutions to this equation. Now let's look at the case when c is still at least 3, but a is less than 3. So a is 1 or a is 2. But let's clean up the whiteboard before we do that. Okay, so we've shown that if c is at least 3 and a is at least 3, there are no solutions. So now we just need to check when a is 1 and a is 2. If when a is 1, let's just plug it in. 2 to the 1 plus 1 is 2 plus 1, which is 3. So the left-hand side is 3b plus 3. And the right-hand side is 6c. 6 to the c, sorry. Again, we're going to use this mod 8 trick. So the right-hand side is congruent to 0 mod 8 because c is at least 3. So this guy is congruent to 0 mod 8. And again, remember we said that 3 to the b is either 1 or 3. So that means when we add 3 to that, it's going to be either 4 or 6. So this left-hand side is 4 or 6, depending on whether b is odd or even. But in particular, that neither of those are ever 0 mod 8, so we get no solutions in that case. What about if a is 2? Well, this is even easier. If we just plug in a equals 2 into the top equation, we get 2 to the 2, which is 2 squared, so 4 plus 1 is 5. So we get 3 to the b, plus 5 equals 6 to the c. But just this equation here, hopefully you can see, this is a multiple of 3, this is a multiple of 3, so that means that 5 must be a multiple of 3, which obviously it isn't, and hence there are no solutions in that case. So essentially, we're considering this equation mod 3. So there are no solutions when a is 1, no solutions when a is 2, and we showed before there are no solutions when a is at least 3, and this is all provided that c is at least 3. And that covers all the cases of A when C is at least 3, and hence there are no solutions when C is at least 3. Hence, we only need to check when C equals 1 and C equals 2. Let's clear the whiteboard and then we'll do those two cases. Okay, so let's firstly look at the case when C equals 1. If we just plug that in, we get 2 to the A plus 3 to the B plus 1 equals 6. Now hopefully it's very easy to see that there's only one solution in this case, and that solution is A equals B equals 1. Because if B was bigger than 1, so if B was at least 2, then 3 to the power of B would be at least 9, and then we have 10 plus some positive number equals 6, which doesn't make sense. So that means that B must be equal to 1, so we get 3 plus 1 is 4, bring the 4 onto the other side, so we get 2 to the A equals 2, so A must equal 1. Okay, so A equals 1 and B equals 1 is a solution. And also, that's the case, C equals 1. So if this is ABC, that's one thing it can be. That's the case C equals 1. Now let's look at the case C equals 2. Well, in this case, we probably have a bit more to deal with, but let's plug that into the equation at the top. So 6 to the C is just 36. So 2 to the A plus 3 to the B equals 36 minus 1, which is 35. And again, we're going to do the same trick. Let's look at B. If B is at least 4, then this guy here is 3 to the power of 4, or at least 3 to the power of 4, which is at least 81, so that's too big. So B must be equal to 1, 2, or 3. So let's look at some subcases. When B equals 1, this guy gives 2 to the A plus 3 equals 35. So that implies that 2 to the A equals 32. So that does have an integer solution. A equals 5. Okay, what about if B equals 2? If B equals 2 now, plugging that in, we get 2 to the A plus 9 equals 35. So that tells us 2 to the A equals 26. But this has no solutions in the integers, so this doesn't work. And what about the case B equals 3? Well, in this case, we get 2 to the A plus 27 equals 35. So that means 2 to the A equals 8. So then that, of course, does have an integer solution. A equals 3. So we collect off two solutions in this case, so we can add them to our list. So we had 1, 1, 1 from the case C equals 1, and the case C equals 2. When we split it up into two cases, one of them we got A is 5, B is 2, and C is 2, sorry. And the other one we get A is 3, B is 3, and C is 3. Yes, like so. Oh, sorry, this is supposed to be A, B is 1. Okay, so those are our three solutions, and those are the only solutions in the positive integers. Anyway, I hope you have enjoyed this number theory video. Thanks for watching. I'll catch you in the next one. Have a great day.